Hello, AP Chemistry students. This is Mrs. Altman. We are on video number 27, Acids and Bases, Part 1. We are in Chapter 14 of your textbook. Here are the objectives for today's video. Pause here. So last year in Chemistry 10HH, we talked about acids and bases, but we only talked about Arrhenius acids. So just in general, an acid is anything that decreases the pH of the solution, and a base is anything that increases the pH of the solution. And there's different types of acids and bases because there's different types of ways for that to happen. So this most simple way is just an Arrhenius acid. It's going to donate a hydrogen ion if it's an acid, and it's going to donate a hydroxide ion if it is a base. So we've got two examples of each. HCl, H2SO4 are both acids, NaOH and NGOH2 are both bases. We're going to introduce a second type of acid this year. It's not super different, a Bronsted-Lowry acid. So the acid is pretty much the same thing. They are anything that donates hydrogen ions, whereas a Bronsted-Lowry base accepts hydrogen ions when dissolved in water. So all the acids that we're going to be looking at are really both Bronsted-Lowry and Arrhenius, at least for the most part. But the bases is where they'll be different. So I have an example here, NH3, that's ammonia. That's something you've seen pretty frequently. And NaC2H3O2, more on that one later, that is sodium acetate. Pause here. So HCl in and of itself is not acidic. It has to react with water for that to happen. So I have HCl plus H2O as a liquid, forming H3O plus and Cl minus. Or any acid takes on the general form of HA, just H plus any sort of anion, plus H2O, yielding H3O plus and A minus. I included equilibrium arrows in the second one because this applies both to strong and to weak acids, which we're going to talk about in just a little bit. Pause here. So if you have a strong acid, that means 100% dissociates in water. That's the reason why I just used the forward arrow in the slide prior, because HCl is a strong acid, whereas weak acids only partially dissociate and they come to equilibrium. So the strong acids are not limited to the ones that I've listed here, but you do need to have these ones memorized. Actually, add to this list sulfuric acid. I will do that right here. So these I do expect for you to be familiar with. If you see them, you can assume that it is a strong acid. That will typically make the problems that you're looking at a little bit easier. Pause here. So when you hear the term conjugate base, this just means the product of this acid reacting with water. So HCl, when it loses one proton, it just becomes Cl minus. HC2H3O2, that's acetic acid, it becomes C2H3O2 minus or acetate when it dissociates. NH4 plus, that is ammonium, a very weak acid, becomes ammonia without the H plus, or just more generally, you have HA and then you have A minus. So the conjugate base always has a charge of one less than the acid. Pause here. All right, I'm going to work through this one with you. Okay, so before you do any sort of problems like this, it sometimes helps to just write out the dissociation reaction. So based off of the dissociation reaction, I can just take what's left over, and that's my conjugate base. Now for the second part of the problem. I'm actually going to need to make an icebox. I'm just going to more generally label my icebox for the sake of time. So I just do HA, H2O, A minus, H3O, and A minus. Okay. Okay. So and notice how the equilibrium constant was given in this problem. So before I actually do that, I'm going to go ahead and write out the expression for Ka. Notice how I don't put water in there, and the reason why I don't do that is because water is a liquid. So I know that my initial concentrations are going to just be all 1 over here and then 0 over here. So H2O, that is not a aqueous or a gas, so I can actually delete the column, or normally if I'm writing this out, I just put a big X through it. I don't really need to do Q, calculate Q here. It's pretty obvious that things are going to be moving to the right. And then this problem actually isn't super difficult to solve mathematically because of the fact that it's just x squared, but you really don't have to do that. So since Ka is so low, I can assume that 1.00 minus x is approximately equal to just 1.00. So that takes this whole problem and makes it a whole lot easier. I can just make this 1.00, which just makes x a whole lot easier to solve for. So I end up with 0.00420 molar, and that is my hydrogen ion concentration. Great, here's the practice set, problem set for today's video. Thank you so much for watching and have a great night.